don't see you, just yell out your question. Let me know. Yeah.
Have you accidentally gotten finger grease on your samples?
I have. And I've also had people bring samples and they just handed them to me with their bare hands. So.
With their finger grease?
Yep. So what you can do is you can grab a wipe with some alcohol and clean it off. Or if it's already too late and it's been in there and you start getting contamination, this unit right here is an oxygen plasma cleaner. So what happens is during the pump down, it bleeds in gas and it bleeds in air and it ionizes it, and the oxygen radicals go in and they help scrub the chamber and clean it up. So we run it every once in a while anyway. Good question. So this is kind of a diagram of how the main part of this works. So it's a cutaway through this column and the chamber. And the idea is this up here always stays under a really good vacuum, and it's actually always on. There's a sharp metal tip and a plate near it, and if under vacuum you apply a large voltage between the two, you can start pulling electrons off that tip. There's a hole in the plate so they pass down through, and there's about a microamp of current coming off of that. And then we select some of that, and we send it through this series of lenses and apertures to get it down to a nice tight beam. In this system, when the beam hits the sample, and it's well focused, it's about a nanometer across. So that's basically the resolution of the system, is how small of a beam you can make it. Once it hits the sample, there's actually a lot of stuff going on. This diagram on the left shows you there's electrons that just get backscattered, there's electrons that get kicked out of the sample, there's X-rays generated, there's a lot of energy. This is actually a radiation producing machine, but we've got an inch of steel all the way around everything, so we're totally safe. We are primarily going to be looking at these re-emitted electrons. So electrons come in with a lot of energy. They're accelerated between 500 volts and 30,000 volts in this system. So they start getting really going fast towards the end. And they slam into the electrons that are already in the sample and they knock them out of their orbitals. And those pick up a bunch of energy and they knock other electrons out of their orbitals. And this excitation volume of electrons that used to be bound is buzzing around in there. If there's a surface nearby, they can escape. And the more surface area you have, in this diagram here, the more electrons you get out, the bigger signal you get. And we collect those at the detector. And this whole thing works kind of like an old CRT monitor, where the electron beam goes and sits at a point for a little while. You get information from there, then it goes to the next pixel, then it goes to the next pixel, and you can construct an image by scanning across the sample that way. And then we have the scan being generated. And in reality, this happens many times a minute, and you can change the rate, and we'll play with that a little bit today. And we're also, in addition to this, like you saw, we're going to be looking at the electrons that go through the sample. So it's going to be kind of a negative image like an X-ray, where we can see different areas of density. So let's go back to this view. Cool. Let me close that. So now the vacuum is good. And this is actually our first sample. So the 2 is just telling me which one it is. And here's the grid I was talking about. So that is copper. And if I zoom in, and so when I'm focusing, I'm using these knobs to focus the beam. In an optical microscope, you guys use microscopes? What have you looked at in an optical microscope? Someone? Pencils. Plant cells. Got it. Makes more sense than pencils. I've actually got a pencil on an SEM demo sample of it. Yeah, you can see small stuff. And when you're focusing those, you're either moving the sample or you're moving the microscope head relative to the sample to get your area of interest right in the focal point. In this system, we can change the strength of the lens rather than moving the sample. So it's actually a lot more like the human eye, where you can focus closer or further away by bending the lens. The lens is, in this case, not a piece of glass or plastic, it's magnetic fields. So there's an arrangement of solenoids around the column, and you run current through them, and you can create a field that focuses the beam. And just by changing the amount of current running through it, you can focus the beam more or less strongly and focus down the road. So right now, I'm focusing on this bit of copper. And the reason for that is I want the microscope to know where the sample is. So by focusing on it, I know the distance, and I can lock that in And basically, this is the safety mechanism that stops you from damaging the microscope. The easiest way you can break it is by running your sample into all this stuff up here, and you really don't want to do that. And now I do want to move the sample up, and I'm not doing that to focus it. I'm just doing it so that the distance the electron beam travels is a lot shorter, and there's less chance for it to hit stray gas molecules or to get scattered by stray fields. So I'm going to move this up so it's nice and close, but still not hitting anything. Focus a bit. And so this quadrant is just showing us these green emitted electrons. So we're seeing a lot of signal from where the copper is, not so much from where it isn't. And then down here I'm going to fire up the transmission detector. That looks right off the bat, it doesn't look great. I'm going to change the value to the There we go. So you can see how we get more signal where there's a gap and less signal where there's a copper. Find some samples. So what should these samples be?
The first sample is cadmium selenide dots, and then 2 and 3 are gold nanoparticles of different sizes, and the last one's graphene quantum dots.
Okay, so 2 is B2, is that right? Or is 2 A3?
The second sample was B.
Okay. I put them in A1, A3, B2, B4.
Okay.
So, okay. Let's go to the gold ones.
Yeah, those might be the easiest
Yeah.
to see.
Yeah.
I'm not sure about the GQB there. Well, I think quantum, I'm not sure you can see it.
Yeah.
Let's try.
Huh. I don't see a film on this grid. Let's look at. These are weird looking grids.
Copper.
Finger green?
Well, one, I don't see a film there at all.
Look for different grids here.
And there's also a lot of particle deposition on the
Copper.
support. Let me look at the fourth one.
This is another one.
It's gone.
Yeah, something.
Yeah, did these grids come out of different boxes originally, or were they all in that box?
All put in the same box.
Weird.
I just opened the package.
Weird, okay. Let me go back.
Typical track record for us.
It was all last one. They put blue dye in the water because we didn't actually have any dots.
Look at her upside down relative to the other one. Normally you don't see there's not a crystal material on there. They'll typically just look like this, and here you can clearly see the film is there. It's like electron transparent, but it's still there. Let's start with this one, and then we'll experiment with the other one more. We got something. This is back to the first sample.
Okay.
Yeah, I mean, so.
And this,
What are these again?
That's might be a conglomerate of cadmium selenide.
Giant masses.
Cadmium selenide moment.
yeah, so this is definitely an aggregate of something.
It's actually good. What's the scale value?
So one thing you'll notice is I'm doing a slow scan now. And that's the main point of that is to average out the noise. So when we're doing those fast scans to move around, it's helpful because it updates quickly. but there's a lot of speckle in it. And then this is better.
Hmm.
I'm gonna say
Nice.
Yeah, those are
Samara, you know if we're getting ours imaged or...
The Vita? You have a USB?
Wait, I thought we had samples though.
Sorry?
Do you have a USB?
I can also
Oh.
email it.
Oh, that's good. Can you email to the Vita?
Sure.
When was that
no, it might
mentioned?
be like the old
And so in these images, here's the 1 micron scales are. And I can also throw on some measurements.
She's supposed to like at the beginning of the exam.
Model.
At the beginning of the lab and
And so these guys have a characteristic dimension of about 100 nanometers. They're kind of wiggly and fancy shaped, but
That's nice.
let's look and see if we can find some individual particles. Or something that's also not right on the edge. So this is partially blocked by where the copper comes in.
Right there.
One thing that might help is to do a bigger scan like this. This instrument's about $1 million. If you didn't have the ion beam and the gas injectors and the various extra accessories, it'd be more like $250,000. So it's kind of tricked out. Look at that thing.
So you know you said like you can like make it by like doing some fluid.
Yep.
So how much does it cost to like fix it?
It depends on what you do to it. So we have a service contract for anything that kind of breaks routinely and not intentionally. They come and they'll replace the consumables, stuff like that. That costs about $80,000 a year. So that's not fun. But if you took a hammer to it and you whacked the wrong part, you could easily do $100,000 worth of damage. This is not your particle. This is some kind of contamination. So I'm going to move on to. That's really not uncommon. You bring these out in room air, you're going to be picking up a little dust no matter what you do. Let's look here.
Oxygen masks.
These are
Let's go. No, it's an actual double.
No, I guess we're not getting our sample. You know what's funny because I was gonna do that section.
No?
Yeah. This might also be something else. Look.
Yes. See the blue bar? Look on the
One
right.
question, what solvent were these in?
It says 30.
That doesn't matter. I have had people put it in like some crazy solvent that just dissolved the
I
grid.
think that's air.
W.
Exactly with there.
So for the chem,
That's probably a piece of land.
the Vita, so for the chem insert, what solvent you have?
Sorry?
Yeah.
For the chem insert, what solvent is it?
Oh, maybe, yeah, true. It wasn't
Hexadecimal.
water. Yeah, I didn't read it out. So let me see when it was.
Because the first grid survived, but the remaining three look like the film is just gone.
The first grid is the one that was not water.
Okay.
The other ones were water.
Interesting. Okay.
Water should be fine.
That's interesting. I'm gonna keep looking. But just to show you what human hair looks like, this is
Kiselin is pretty
This actually
fascinating.
A company that uses this once in a while. This is peroxide damaged hair, and the cuticles have been torn up. So that's why it's kind of peeling up in places. And they make a product that's supposed to heal it. So that's like the before picture. We don't have it yet.
Wait, but who puts hydrogen peroxide in their hair?
If you're dyeing your hair,
Oh.
That's what my hair looks like.
So the beta